Hello and welcome. In this video, we're going to learn some fundamental trig identities. Some of them we already know, some of them we're going to build on, some of them we're going to derive. But we're going to focus on some fundamental trig identities, how to use those identities to find the other 6 trig functions, and how to use those identities to prove or verify that something simplifies to something else. So using them within proofs. So let's go ahead and jump right in. All right, so here we have our list of fundamental trig identities. Let's talk about the ones that we already know. We already know, and we started this chapter by defining that cosecant is the reciprocal of sine, and that secant is the reciprocal of cosine, and that cotangent is the reciprocal of tangent. So these 3 are not new. You've been using these 3 all chapter. We learned one more that we also used quite a bit, and that was that tangent of theta is sine over cosine of theta. And we've been using that one quite a bit as well. This next one over here is just the reciprocal of that. We know that tangent is sine over cosine. We know that cotangent is the reciprocal of tangent, which means that cotangent must be cosine over sine. So just as if we flipped these 2 things to come up with this trig identity. The next one is one of the ones that gets used a lot in higher level math classes, and that is that sine squared theta plus cosine squared theta equals 1. And let's talk about where that comes from. So if we drew the unit circle, pretend this is a perfect circle, and we drew a triangle on the unit circle. We know that every point on the unit circle is cosine comma sine. So I'm going to just redraw this triangle out here. So this length x is cosine of theta. The height of this triangle is the y value, which is sine of theta. And since this is the unit circle, we know that the hypotenuse is 1. So this relationship just comes from the Pythagorean theorem. This side squared plus this side squared equals this side squared. So sine squared plus cosine squared equals 1. This is a really important one. If we know this one Pythagorean identity, we can actually come up with 2 others, and I'm going to show you how to come up with those. So what if we took each term, I'm going to do this down here, what if we took each of these terms and we divided them all by cosine squared? So if I divided this by cosine squared theta, divided by this by cosine squared theta, and divided this by cosine squared theta, sine squared theta over cosine squared theta is going to give us tangent squared theta. Cosine squared theta over cosine squared theta, anything over itself is 1. And we know that 1 over cosine is secant, so this is going to be secant squared theta. So we can actually add another trig identity in here, another Pythagorean identity in here. Now if we do the exact same thing, but instead of dividing by cosine, we divide everything by sine squared, go ahead and simplify that and see what you get. Well, sine squared divided by sine squared is 1. We just learned that cosine squared over sine squared, or cosine over sine, is cotangent. So if they're both squared, then it's going to be cotangent squared. 1 over sine is cosecant, so if sine is squared, that must be cosecant squared. So now we have another one. Now really, you don't have to memorize these 2 as long as you know this one, because you could always come up with them. This didn't take a ton of work for us to derive these other 2. Oftentimes I can't remember which ones go together, and so I'll just say, okay, let me just divide everything by sine squared and see what happens. Divide everything by cosine squared and see what happens. But you will be expected to use all 3 of these. So if you don't memorize all of them, if you only memorize this one, make sure you know how to come up with or how to derive the other 2. The next type of fundamental trig identity that we're going to use in this class is the cofunction identity. And what the cofunction identity says is that sine and cosine are really just shifts of each other. So if you think about how the curves are formed, a sine graph starts at the center, goes up, and comes back down. But if we just shifted and started our period here, we would end up with a cosine graph. So that's the idea, and that's why when we focused on writing the functions from a graph, we talked specifically about starting at the x-axis and not focusing on shifts left and right, because technically every one of those functions could be written as a sine function or a cosine function, depending on where you're starting a period. So all this is saying is if we shift sine slightly, we get cosine. If we shift cosine slightly, we get sine. And notice those are the same shift. Sine of pi over 2 minus theta is cosine. Cosine of pi over 2 minus theta is sine. So those are functions that you should know. You can translate between those two forms, which also means we have a similar relationship between tangent and cotangent, which is that tangent of pi over 2 minus theta would give us cotangent. Again, just that one slight shift. Lastly, we're going to talk about negative angle identities. Negative angle identities really just come from the idea of what happens if we reflect. So let me actually clear some space so that we can look at the graph of sine and cosine and think about what happens if we perform a reflection. So here's our graph of sine, and what I'm going to do is I'm actually just going to add another period to it going back in the opposite direction. And I'm going to do that in this blue color so that you can see. So this identity here is saying what happens if we reflect sine across the y-axis. So if I reflected sine across this axis here, or if I folded it across that dotted line, this point is going here, this point is going here. So each of our points, they're not landing right on top of each other, they're flipping. So what was up is down and what was down is up. And because of that, that's a reflection. So if you think about it, if I took this point and moved it down here, if I took this point and moved it here, now I have a negative sine function, which would be upside down. So what this is saying is if we reflect sine across the y-axis, we take the opposite of the entire function. Let's think about what happens with cosine. So here's my regular graph for cosine. I'm going to go ahead and plot another period so that we can see what's happening. Wow, that was not very good, but we can see what's happening if we again reflect across the y-axis. Well, if we reflect across the y-axis, this point is going to be here and this point is going to be here. These 2 points are going to switch places, which means really everything is just landing on top of each other. So if we reflect cosine across the y-axis, which is what happens when we have that negative inside our function, everything is really just landing on top of itself, which is why cosine of negative theta is equal to cosine of theta. Since tangent is sine over cosine, you can see where this last property is coming from, just this divided by this, which would be the opposite of tangent or a reflection in the x-axis. So now that we've talked a little bit about what the fundamental identities for the trig functions we need to know, we're going to talk about how can we use these. We're going to tie this back to a concept that we've learned before about finding the 6 trig functions, and then we're going to talk about how can we use these to verify trig identities. Okay, so the first thing we're going to do is we're going to be given one trig identity, and we're going to be asked, and a quadrant. I want to point out we're told that we are given this quadrant, which quadrant is pi over 2 to pi. It's this quadrant here. That helps us remember what's positive and what's negative. We learned in a previous lesson the acronym all students take calculus, which means in the quadrant that we're talking about for number 1 here, sine and cosecant are the only things that are positive. Everything else is going to be negative. Now, what we learned in previous lessons is that we could just draw a triangle and we could figure out that this is 4 and this is 5, and we could use the Pythagorean theorem to find the missing side, and then we could find the other 5 trig functions. What we're going to do in this lesson is we're going to use a trig identity. Typically, we're going to use a Pythagorean identity to find another trig function, and then we're going to use that information to find all 5. So if we start with sine, I'm going to just point out we also know that then cosecant must be 5 over 4. We don't have to do any work to find that. So now what Pythagorean identity involves sine? Sine squared plus cosine squared equals 1. So let's plug in what we know. We know that sine is 4 over 5. So 4 over 5 squared plus cosine squared equals 1. If I square that, I'm going to get 16 over 25. Since I know eventually I'm going to have to move this to the other side, I'm going to go ahead and rewrite 1 as 25 over 25 so that I have a common denominator. Then I'm going to subtract 16 over 25 from both sides. So 25 minus 16 is going to give me 9 over 25. If I square root both sides now, I'm going to get that cosine of theta is 3 over 5. And I need to check and make sure which quadrant this is in. We said that we were in this quadrant, which means that cosine should be negative. So we're actually looking at the negative square root of 9 over 25, which is going to be negative 3 over 5. If we know what cosine is, then we also know that secant is just going to be the reciprocal of that. And if we know these three, we could either use the fact that tangent is sine over cosine to figure out the value for tangent, or now we know all three sides of the triangle, so we could find it in that way. But I'm going to use the fact that tangent is sine over cosine. So tangent of theta is sine of theta over cosine of theta, which means in this case, we have 4 over 5 divided by negative 3 over 5. So tangent is really just going to be negative 4 over 3, which means that cotangent will be negative 3 over 4. These 5s are just dividing out. So I understand that this is totally different and maybe more challenging than just drawing a triangle, but what we want to, the reason we're doing it this way is to practice using these different trig identities to make what's coming a little bit easier. Okay, number 2. We are in the quadrant between pi and 3 pi over 2. That's down here. That means that tangent and cotangent are the only things that are positive because all students take T for tangent. Calculus, the only thing that's positive in that quadrant is tangent and cotangent. Okay, so now I'm going to say what I know secant is. Secant is going to be negative 5 over 4. Get that one out of the way. And now I'm going to use a trig identity with cosine. So I'm actually going to use exactly the same trig identity that I used on the last problem. Sine squared plus cosine squared is 1. So sine squared plus negative 4 over 5 squared equals 1. So sine squared plus 16 over 25. And again, I'm going to go ahead and rewrite this as 25 over 25. Sine squared is going to be 9 over 25. So sine of theta is going to be the square root of that, which is 3 over 5. Double check your quadrant. Everything is supposed to be negative except for tangent and cotangent. So that means that sine is going to be negative, and it means that cosecant is going to be negative as well. Now to find tangent, we know that tangent is sine over cosine. So in this case, tangent is negative 3 over 5 divided by negative 4 over 5, which is just going to be positive 3 over 4. Which means cotangent is positive 4 over 3. Now that we've talked about how to use trig identities to do something that we really already knew how to do, which was find the other 5 trig functions given 1, let's extend this idea to simplifying trigonometric expressions. Okay, so here we have some expressions that involve different trig terms. And what we're going to do is we're going to use a variety of the properties that we just discussed, the different trig identities, and we're going to use that to help us simplify. So our ultimate goal is to simplify everything down to be just one function or one term. So when I look at number 3, the first thing I like to think about is what's the most complicated looking part of what we have here? And the most complicated looking part is this. The other piece, sine. Sine is one of the functions I feel pretty comfortable with. Sine and cosine usually make things simplify out nicely. So I'm going to ask myself if there is another property on that list, and it's okay to look up at that list, is there another property that allows us to change tangent of pi over 2 minus theta to be a different function, maybe a simpler function? So if you look at that list, the identity is that if we shift tangent pi over 2 minus theta, we end up with cotangent. So if we just substitute in cotangent for that tangent piece, then we are left with an equivalent expression of cotangent of theta times sine of theta. Now, I know that cotangent can be expressed in terms of sine and cosine. So what could I change cotangent to so that it is in terms of sine and cosine, in hopes that one of those signs may simplify with the sign I already have? So cotangent, looking at those properties, is equivalent to cosine of theta over sine of theta, which means now we have a sign in the denominator and a sign in the numerator that can simplify, and I have gotten this down to be one term. Okay, let's look at number 4. When I look at number 4, the first thing that I notice is that both of these terms have a secant. I also notice that I have tangent squared, and I know that there is a Pythagorean identity that involves tangent squared, but I think the first thing I want to do is maybe just separate secant out. So what I'm going to do is I'm going to factor out the greatest common factor. What do both terms have in common? They have a secant. If I factor secant out, what's left is tangent squared theta plus, well, if I factor secant out, all that's left here is 1. Anytime I see 1 and something squared, I think I might have a trig identity. So go ahead and look and see what trig identity is tangent squared theta plus 1. And hopefully you can see that that is secant squared theta. So I have the secant that I already had times secant squared, which if I multiply them will give me secant to the third of theta. So now I have everything in terms of one function instead of having this sum of two different terms being added together. So a lot of the things that we're talking about come from algebra. What do we do here? We factored out the greatest common factor. What do we do here? We substituted in something else for this tangent piece. So thinking in an algebraic term, when I look at number 5, the first thing I notice is I have 1 in cosine. That makes me think of sine squared plus cosine squared equals 1, but I don't have cosine squared. The next thing I think about is I have these two sets of parentheses. So I wonder what would happen if I just distributed out these two sets of parentheses. And this is the difference of squares. So when I do that distribution, the middle term is going to add to be 0. So I'm going to pretend that I didn't notice that. I would get 1 plus cosine theta minus cosine theta minus cosine squared theta. And these two cosines in the middle are going to simplify. So by multiplying, we just end up with 1 minus cosine squared theta. Now, what do I know about 1? I know that 1 is equal to sine squared theta plus cosine squared theta minus the cosine squared theta that was already in this problem. And now, do you notice anything? These two terms are going to add to be 0. So what are we left with? We're left with just sine squared theta. Again, we have simplified down to one term. Okay, number 6. I want you to pause the video and see if you can come up with an idea on how to work through this on your own, and then unpause the video and see how you did. All right, hopefully you've had time to experiment with this a little bit on your own. I think there's a variety of different approaches. The first time I did this problem, I actually changed cotangent into cosine over sine and tangent into sine over cosine, and then I found a common denominator, and I worked with everything in terms of sine and cosine. And I think I did it that way because I feel really comfortable with sine and cosine. Looking at it now, I'm kind of wondering what would happen if I just rewrote cotangent as 1 over tangent, and I'm going to rewrite tangent as just tangent of theta over 1. If I want to combine these into one term, since my ultimate goal is to get down to one term, I need a common denominator, and that common denominator would be tangent. So I'm going to keep the first term the same, 1 over tangent of theta, plus now I have tangent squared theta over tangent of theta. And since they have the same denominator, I can now write this as one fraction. Now, do you see anything that looks like a trig identity? Hopefully, you noticed that this looks like a Pythagorean trig identity. 1 plus tangent squared, we actually use that same identity in number 4, is the same thing as secant squared of theta. And if I want to move tangent of theta into the numerator, 1 over tangent is just cotangent, so I could rewrite this as secant squared of theta times cotangent of theta. Now, to see if this simplifies any more, we can rewrite what we know cotangent of theta is. Cotangent is cosine of theta over sine of theta. Does this simplify? Is there anything we can change secant to? Well, secant is 1 over cosine. So this is going to be 1 over cosine squared theta times cosine of theta over sine of theta. So one of these cosines can divide out, and we're left with 1 over cosine theta sine theta. And maybe we can look at the reciprocals of those two functions so we don't have this fraction. 1 over cosine is secant, and 1 over sine is cosecant. So there's a lot of different ways to get here. And the thing I don't love about this particular problem is I ended up having 2 terms still. No matter what I do, I still end up with 2 terms. These problems are a lot like a puzzle. You get better at them the more you practice them, the more you work with the different properties, you learn the skills, and you learn what strategy works best for you. One of the things that I love about puzzles, regular old jigsaw puzzles, is that usually when you're doing a puzzle, you have the picture, the box, and that's the last type of problem we're going to talk about in this lesson. We're going to talk about verifying trigonometric identities. All right, so we can use the trig identities that we already know to verify that other trig identities are true or that other things are equivalent. This is sort of like doing a proof. And when we do a proof, what we're really doing is we're trying to take one side of the equation and manipulate only that one side to make it look like the other side. So when I think about jigsaw puzzles, I know the picture, and the picture always looks like this beautiful, well-composed thing that I'm going to end up with. If I open the box and I see all the pieces, it kind of looks like a hot mess. So when you look at these problems, I want you to identify what's your hot mess. So this looks like my hot mess here on number 7. The beautiful picture looks like sine squared theta. So what I'm going to try and do is I'm going to try and manipulate the purple side until it becomes sine squared. So the first thing that I'm thinking is that I have secant squared both in the numerator and the denominator. So I wonder if I split this so that each term in the numerator is its own individual fraction, which I know from algebra I'm allowed to do. Does that help me at all? So let's see. This is going to turn into just 1 minus 1 over secant squared theta. And what is 1 over secant squared theta? Well, that's the exact same thing as cosine squared. And I know I would like to get rid of a fraction because there is no fraction on the picture side, the sine squared side. I know that my ultimate goal is to get down to be sine squared theta. So I'm trying to manipulate the left-hand side to get down there. Okay, well, I see a 1 and I see a cosine, and that tells me I can use a Pythagorean identity that sine squared plus cosine squared is going to equal 1. So minus the cosine squared that was already there. So now these two cosine squareds are going to add to be 0, so I'm left with sine squared theta equals sine squared theta. And I know that I'm done because I got to the place that I was supposed to get to. Okay, let's look at number 8. Which side of the equation do you think is the pretty picture side, and which side do you think is the complicated jigsaw mess? For me, I think this side looks more complicated, and it is totally possible for you to think that the left side looks more complicated and for you to manipulate the left side until you get it to be the right side. That's fine. You're just only allowed to change one side of the equation and make that side become the other side. So I'm going to work with this fraction. Now, I can't split this fraction like I did on number 7 because the denominator is the part that has more than one piece, not the numerator. So I'm trying to figure out, how do I deal with this 1 minus sign in the denominator? And one of the tricks that you'll learn the more you practice this is if you see 1 minus something like this in the denominator, oftentimes multiplying by the conjugate is going to get you to a better place. So I'm teaching you a trick right now. With this fraction, I'm going to multiply by the conjugate. When I do that, I'm going to end up with 1 minus sine squared x in the denominator of my fraction if I multiply out those difference of squares. Well, what happens if I substitute, kind of like I did on this last problem, in for 1, if I plug sine squared x plus cosine squared x, because I know that sine squared plus cosine squared is 1. And I'm going to keep in red what was already here. And notice these sine squared x's are going to subtract to be 0 now. Numerator is going to stay the same. Now in the denominator, I have cosine squared of x. So I have 1 cosine over cosine squared. That's going to simplify to be 1 cosine left, and that cosine is going to be in the denominator. And in the numerator, I have 1 plus sine of x. Now I can split the fraction, 1 over cosine plus sine over cosine. And 1 over cosine is secant, and sine over cosine is tangent, and that's where we were supposed to get on this verifying problem. All right, I'm going to encourage you to try number 9 using a similar property to what we just did. So think about conjugates. Then I'm going to encourage you to try number 10 and think about getting rid of those fractions. How could I move cosecant and secant to the numerator? Then unpause the video and see how you did. All right, so here's my recommended first step for each of these problems. See if you can now simplify either of them. Think about Pythagorean identities to help yourself get the rest of the way through the problem. So on number 9, for eventually getting to secant of theta plus tangent of theta, and on number 10, eventually getting to 1. Okay, for number 9, we know a property, I'm going to just write this up here, that says that tangent squared theta plus 1 equals secant squared theta. What that means is if I subtract this on both sides, that 1 is equal to secant squared theta minus tangent squared theta. So I'm going to substitute that into the denominator here. So I'm going to keep the numerator just as secant of theta minus tangent of theta, and this whole thing is going to become divided by 1. And look, that actually is what we were trying to get to. Yes, there are other approaches that would get you to the same place. All right, I'm going to multiply here on number 10. This is sine squared plus cosine squared, which is 1, which is what we were trying to prove. So there's a lot to digest in this section. Just understanding where the properties come from, understanding how to use them to determine the other 5 trig functions given just one, and thinking about the quadrant, then talking about verifying and simplifying with trig expressions. Don't be discouraged if this feels a little overwhelming at first. Do a couple problems each day. The more you work with this, the better you'll get at it. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.